Good morning, Panthers. This is Dr. Augustine, and today we are going to be talking about precipitation reactions. Precipitation reactions are one of the three big classes of aqueous reactions. And what is a precipitation reaction? Well, you've heard of the word precipitation, and that's used when it's raining outside. So that's when you have something in one state of matter, like, for instance, in the gas state, and coming out in another state of matter, like the liquid state. So when it rains, and we say that it precipitates. We can do the same thing with two things that are in the liquid state. We can have aqueous solutions of some compounds, mix them together, and do something like this where it forms a solid. So the solid is called the precipitate because it is precipitated out of solution. This particular one is a very dramatic example. This is actually lead iodide. We'll talk about the reaction here in a minute. And if you go on YouTube, you can look up some examples of what's called the golden rain reaction. So if you go on YouTube and you type in golden rain precipitation reaction, you can watch a video of this actual this process taking place, this lead iodide reaction taking place. So it starts with two clear solutions. One of them is potassium iodide, Ki. The second one is a solution of lead nitrate, PbNO3. You react those together, you get this yellow compound forming called lead iodide, and you also get potassium nitrate as your other species that are in solution. And so kind of on a molecular scale, what you would see is potassium ions, which are represented here with gray, and iodide ions, which are represented in the bluish purple. And then, of course, there's water molecules in there as well. So that's your solution, Ki. And it is soluble. We'll talk about how you know whether it's soluble in a minute. And then in the other solution, we've got lead 2+ ions represented in the golden color, and we've got nitrate anions, NO3-. Remember, that's a polyatomic anion. That one is also soluble, means it dissolves in water, and so we have the water molecules in the background. So they are dissolved and separated from one another. When we dump them together, what we find is a solid forms of lead iodide, PbI2, and you notice it's got a regular structure, that's a crystalline structure. We also end up with these ions in solution, K+, NO3-, and then there's the water molecules in the background. So the lead iodide is insoluble, the lead nitrate is soluble, and that's sort of a molecular picture of what's happening in this chemical reaction. All right, so we got a couple of names we want to define. The first one we will call the precipitate. And that is the species that forms the solid when the reaction occurs. And basically you can think of this as this is the thing that is insoluble in solution. In this particular case, it's PbI2. So you may have a question on an exam that says, which of the following, what would be the precipitate given the following reaction? And then the other term which we use are called the spectator ions. Spectator ions are not actually involved in the chemical reaction. They're just like a spectator event at spectator at a sporting event. They're sitting in the stands watching the game going on, but they're not actually involved in the play while it's happening. So the spectator ions for this particular reaction are the K+ and the NO3- ions. Neither of those are actually involved in the chemical reaction. We could have actually picked different spectator ions if we'd started with different solutions. So those are the ones that end up here in solution, still dissolved, not part of the chemical reaction. They're called the spectator ions. Okay, so a logical question at this point is, how do we know which thing's going to react and which thing isn't? So that is where we invoke something called the solubility rules. Okay, so in your textbook in table 4.1 in Tro's text, there is this kind of ridiculous looking table that you can memorize that tells all the different solubility rules. And let's just start with the species that we have. We have Ki, we have PbNO3, 2, we have PbI2, and we have KNO3. Those are my 4 different reactants. Now you might also be wondering, well, how do I know what these reactions are? So let's talk about the general form of these chemical reactions before we figure out the solubility rules. So we have something like this, Ki, and we know this is an aqueous solution, plus PbNO3. That's also an aqueous solution. We're told that it's aqueous. And then it forms some products. And here's how you approach this. This is called an exchange reaction or a metathesis reaction. So what that means is the cation from one species exchanges with the anion from the other species, and the cation from this species exchanges with the anion from the first species. Okay? So what we do is we take cations and anions and we swap them. So then we end up with, on the product side, PbI2 plus KNO3. All right, and this is where the solubility rule comes into play. So what you do is you look at the solubility rule and you say, for instance, Ki, is that going to be soluble or not? Now, I already wrote aqueous, but we can use the solubility table to help us understand that, and it says lithium, sodium, potassium, and ammonium ions are generally soluble. Okay, so this has a potassium ion, therefore it must be soluble. Nitrate ions come here, nitrate and acetate. Those are also generally soluble with no exceptions. Okay, so since nitrates are soluble, well then this also must be aqueous, which tells us immediately we've got a K plus ion here, we got a nitrate ion here. We know that these are generally soluble. Therefore, we can write next to this, oops. We can write next to the potassium nitrate that this is aqueous. Now, how do we know if potassium iodide is insoluble? So then we come back to this table and we say, let's see, let's find something. Oh, there's iodides right there. Well, they're generally soluble. So maybe that's soluble, except you read the exceptions. When these ions are paired with Pb2+, then they are insoluble. Okay, so that just tells us this must be the solid. So this is the way this table works. You would take each species, 1, 2, 3, 4, and then you would go into the table and say, is it going to be soluble or is it going to be insoluble? Potassium ion, okay, it's going to be soluble. Nitrate ion, that's going to be soluble. This one's got potassium and nitrate, that one's going to be soluble. This one's an iodide, which are generally soluble, except when it's paired with a Pb2+, it's insoluble. All right, so that's how we actually use the solubility rules. So just to quickly wrap up what we've talked about, we have these solubility tables, which we can use for any pair of ions, and the general rule is we take the reactants, whatever they are, and we do an exchange reaction. We take the cation from one, match it up with the anion of the second, cation from one, anion the other, and we write the products as the exchange products. Now you may be noticing right here, hey, wait a minute, this isn't balanced. That doesn't change the way we approach this, but it does change. We really need a 2 here and a 2 here, and then it's going to be balanced. Okay? So the general strategy then, exchange reaction between the reactants and the products, and using the solubility tables then to predict, is this going to be a solid or is it going to be aqueous? All right, so that previous table is a little bit confusing. There's a lot of things to memorize. If you're trying to memorize that table, it's a little bit confusing. So here's a little bit of a simplified solubility rules. It's a little bit of an easier way to look at that same table. Now, it is simplified, does not have all the same information that the other table has, and we'll find that out in a second just using the example we just used. But this actually makes your life quite a bit simpler if you look at this table right here. So here's how to read this table. If there is a clear space, no colors in it, that means it's soluble. So here's how to attack this. Group 1 cations and ammonium ion. If you see a group 1 cation or an ammonium ion, no matter what it's attached to, it's going to be soluble. Therefore, we know that potassium is soluble. We know that potassium iodide is soluble. We also know that potassium nitrate is soluble. All right, so group 1 cations, always soluble. Nitrates, always soluble, no exceptions. So therefore, this must also be soluble. And we write an AQ next to it, aqueous. And then of course, this one has both the nitrate and the potassium ion. So of course, that's going to be soluble as well. Now, if you look at this table, you notice it doesn't have as many ions on it. It has nitrate, chloride, sulfate, hydroxide, carbonate, and phosphate. And there's no iodides written on here. But if we know it's a precipitation reaction, we can use by process of elimination, we know the rules for this, so therefore this has to be the soluble species. Okay, so there are limits to this table. It is a simpler table, but it's not perfect. For example, iodides are not on there. So you'd have to use by process of elimination. If you're told it's a precipitation reaction, you can still use this table to figure out which one precipitates. Now, a couple other things to note. You might be saying to yourself, well, what are these other things here? So orange means insoluble. So as you see, most phosphates are insoluble, most carbonates are insoluble, and transition metal hydroxides are also insoluble. So the way we read across here is group 2 cations, alkaline earth, and then transition metals here. So transition metal hydroxide cations, those are also insoluble. And then these ones written specifically are exceptions. So magnesium hydroxide is insoluble. Barium sulfate is insoluble. You can see most sulfates are actually soluble, but barium sulfate is insoluble. And for chlorides, most chlorides are soluble with the exceptions of lead, silver, and mercury chloride. Now, again, if you look at that last table, there's even more details about slightly soluble versus soluble. This is a simplified table. It'll get you maybe 85% of the reactions you could possibly come across. But it's a simpler and quicker way to figure out solubility rules.